Okay, first I will start with uh, lifting problem. So, let us see what is a lifting problem. Let P from E to B and F from X to B uh, continuous maps. Continuous maps. The lifting problem, the lifting problem for F is to determine whether there is there exists a continuous map F prime from X to E such that F prime compose P equal to F. That is uh, whether uh, the dotted arrow in the diagram. What is the diagram? You have X, B, B, then you have E here. So this is P, F. This is the dotted arrow. It says that this lifting problem for F is to determine whether there exists a continuous map F prime from X to E such that this is there. That is whether the dotted arrow, right, this one corresponds in this diagram corresponds to a continuous map making the diagram commutative, right? That is if this is F prime, then F prime composed P should be equal to F. If there exists such a map F prime then we say that f can be lifted to E. Right? So this is your E, B, F, B. So if there exists such a map F prime, we say that F can be lifted to E and we call F prime a lifting or lift a lifting or lift of F. Now, so how this problem will look like? So this is a lifting problem in your category of continuous means topological spaces and continuous maps, right? Next, we will see how will be the lifting problem. How the lifting problem is going to look like in the category of topological spaces and homotopy of maps. So lifting problem in homotopy category. A map Fp from E to B is said to have homotopy lifting property. Homotopy lifting property said to have homotopy lifting property with respect to a space X, with respect to a space X. If given maps, given maps F prime from X to E and this capital X F from X cross I to B such that F x0 equal to F prime compose P applied over X for every x belonging to capital X. So if a map P from E to B is said to have homotopy lifting property with respect to its space X, if given maps F prime and capital F such that this holds, uh, there is a map, there is a map that is continuous map, uh, given continuous maps, there is a continuous map capital F prime from X cross I to E such that F prime X comma 0 equal to F prime X for every X in X, and F prime composed P equal to capital F. This homotopy lifting means this is a lifting problem in homotopy category. Now, so we can treat treat X as X this, right? So this is of course homeomorphic. So if we treat F prime to be a map from, so F prime is a map from where to where? It is from X to E. X to E. So we can treat F prime to be from X cross to E, right? Here means you identify X with X comma 0. Okay. Then if we do this, then the existence of F prime is represented by this, you consider X cross 0 to E F prime, and then you have X cross I here, and then you have B, P, and this is your F, prime. So this you can consider as inclusion map, right? Okay, so homotopy lifting property can be considered as given any map P from E to B, capital F from here to here, and F prime from here to here, such that this diagram is commutative, right? This outer, this one. So this diagram is commutative, right? Suppose we are given this, there is suppose we are given a commutative diagram like this, right? Then uh, the homotopy lifting property represents the existence of a map uh, represented by this dotted arrow, right, from x cross I to E, such that this whole diagram is commutative, right? So that is, you have this composed, this is this, you have this composed, this composed with this is this, right? So so here observation first, if P from E to B, if P from E to B has homotopy lifting property, lifting property has a homotopy lifting property with respect to x and f naught comma f1 are from x to b are homotopic, right? So if this has a homotopy lifting property with respect to x, and these are maps from x to b, which are homotopic, then it is uh, then this f naught can be lifted to E if and only if this f1 can be lifted to E. F1 can be lifted to E. So just see that you have here E and your P, V, and your X is here. So F naught and F1, they are homotopic maps, right? It means there is a homotopy, right? It means there is a homotopy capital F such that, right? Now, if F naught is F naught can be lifted, suppose can be lifted to this F naught tilde, suppose. Okay, just a minute. So this capital F will be from X cross I. Right? So it will be from X cross I to here, right? So here uh, this X cross, this is inclusion, right? So this is F naught tilde, right? So if F naught tilde is can be lifted to E, right? Means what? Because P has homotopy lifting property with respect to X, it means what? There will be a map F prime from here to here, right? Such that your F prime composed P is F, right? But then P composed this, you consider this uh, so here F prime X comma 0 will be F naught, right? And then what you have is uh, this uh, you have this uh, from here we can use it here. So this P composed F prime X comma 1 equal to F X comma 1, right? But what is this? This is F1 X, right? Because capital F is homotopy between F naught and F1. And this is what? This is P composed uh, F prime, yeah. So this is you can write it here. This represents F prime X comma 1. This represents a function F1 prime from X to E, right? So similarly, so F naught has a lift, right? If and only if F1 has a lift. What we have proved? We have proved that F naught has a lift implies F1 has a lift. Now, if F1 has a lift, then similarly you can prove that F naught has a lift. Uh, yeah. So, so given a map, suppose P from E to P is map and X. So suppose this map P has a homotopy lifting property with respect to X, all right, then whether or not a map from X to B can be lifted to E uh, is is property of its homotopy class, right? If one map, if one map from, if there is a map from X to B, which can be lifted to E, then all the maps which are homotopic to that map can be lifted to E, right? So that is property of that homotopic class. Next, we can define next we can define a map uh, definition. Definition a map P from E to B is called a vibration if P has a homotopy lifting property, a homotopy lifting property with respect to every space. E is called here if P is a vibration from E to B, then your E is called the total space, and B is called the base space, the base space of the vibration. And for any if we choose any B in capital B, this P inverse B, which is a subset of E, is called the fiber over B. So we have another observation. If P from E to B is a vibration, then any path omega in B such that, so omega we are considering the path in B that is a continuous function from B to 0, 1 to B. B such that omega 0 belongs to P in this image, right? If we have a vibration and if we have a path omega in B such that its starting point omega 0 is in PE, right? Then that any path omega in B such that this is there can be lifted to a path omega prime in E. Right, so how it is, so you can omega is a map from here to here. So actually what you can do is You can treat omega, so you can consider P to be a singleton, right? Right? And you can treat omega to be a map from P cross I to B. Because this P cross I, that is this singleton X naught cross I, this is so of course homeomorphic to I. So this X naught comma T, you can consider equivalent to T. Now you can treat omega to be a map from here to here. Now this uh, there is a point, right? If we assume this condition, it means what? It means that there exists some point uh, uh, y in E such that P of y equal to omega 0, right? So you can define a map omega prime, right? Sorry. Uh, so you can define a map. So here F you can treat uh, F you can treat to be map from P to B, just uh, F of X naught equal to this omega 0, and F prime you can define again from P to E by F prime X naught equal to this Y, right? Then there exists there by, because P is a fibrescence by homotopy lifting property, there exists uh, omega prime from P cross I to E such that omega prime composed P equal to omega, right? So omega prime is from P cross I to E, so it will be equivalent to a map from I to E, right? So basically you have omega prime composed P equal to omega, right? Is following example, uh, if F is any space, then you can define P from B cross F. B is also any space. B and F are any spaces. Then you can define P from B cross F to B by P of B comma uh, uh, X equal to B, for every B belonging to capital B and X belonging to F, right? So you can verify that this is a fibration. So this is just a projection, right? So verify that, P is a fibration. this you can consider as an exercise, simple exercise. Next, uh, I'm going to prove one result. Uh, this is a theorem. Let P from x tilde to x be a covering projection, be a covering projection projection, and let f and g be maps from y to x tilde. Uh, P is the covering projection, and let this be maps which are actually liftings, the liftings of the same map, same map. Uh, right? What does it mean? That is this P composed F equal to P composed G. Right? If Y is connected and F agrees with G for some point of Y, some point of Y, then F equal to G. Right? If Y is connected, then if two lifts of a given map agree at one point, then they will be actually identical. So proof, let Y1 be the set uh, this Y in capital Y such that Fy equal to Gy. So we will prove that this is an open set. So what we'll do actually, we'll prove that Y1 is open, right? And also Y1 complement is open, right? And it will give us a contradiction uh, if this Y1 is not whole of capital Y. So we show that we shall prove that Y1 is open subset of capital Y. Now for this, what we will do for any Y belonging to capital Y1, let U be an evenly let U be an evenly covered open neighborhood of this P composed F Y, right? So it is where it is in the so this is your E, this is your sorry, this is your X tilde, this is your X, this is your Y, right? So this P, this is your, these are the F and G, right? These are F and G. Uh, these are F and G are from here to here, right? So your sorry, F and G are from here to here, right? So if you have chosen Y here, then P composed. So this F and G are from here to here. So P composed F. Sorry, this is F composed Py. This is F composed Py. F composed Py. Y is here. It will be a point here because this is a covering projection. So every point here will have open neighborhood which is equivalently covered. So we have chosen B to be open neighborhood of this equivalently covered by P. Now let U tilde be open set. Let U tilde be an open subset of X tilde. So because this P inverse U is disjoint union of open sets, each of which is homeomorphically mapped onto U by P, right? So because P inverse U contains this Fy, right? So Fy will be one of these disjoint open sets of which P inverse U is made of, right? So let of X prime X tilde containing Fy such that P maps U tilde homeomorphically onto U. Now F inverse U tilde intersection G inverse U tilde is an open subset of Y containing Y and it is contained in Y1. Why? Just see that. Of course, because F and G are open, so F inverse U tilde is open, G inverse U tilde is open, right? So intersection of two open sets is open, right? And Y is here because you see Y was Fy was here, Fy was in your U tilde, but you know that your Y was where? Y was in Y1, right? Y1 at points of Y1, F and G agree, right? So it means Fy equal to Gy. It means what? It means that Y belongs to this as well as Y belongs to this, right? So Y is in U, Fy was in U tilde and this was there. So F inverse U tilde and G inverse U tilde both contain Y, right? So this is an open subset of Y and Y belongs to this. Small y belongs to this. Now, we claim that this is actually contained in Y1, right? So suppose that there is some point here which does not belong to Y1, right? So suppose there is some Y0 which does not belong to this intersection, means what? Means that Fy0, F and G will not be equal on this point, at this point Y0, This is not equal to g y naught. Okay. Then what will happen is uh, now this uh, so but f y naught and g y naught both are in where y naught is here, right? Which does not belong to y1, right? But then if y naught is here, then y naught will be here as well as here. But then f y naught and g y naught, f y naught and g y naught both will be in where u tilde, and p compose this this is what this is actually f g composed p, because there this is there f composed p equal to g composed p, right? And hence this is there. So these points f y naught and g y naught, they go to same point, and where in u, right? So these two are different points, and they are going to a single point in u, right? But p restricted over u tilde, from u tilde to u, it is a homeomorphism, and there are two distinct points in u tilde which go to same point. It means what? It means that p is not injective. So this is a contradiction to the fact that p is homeomorphism. So it means that this is contained in y1. So what we have done, we have chosen a point in y1, right? We have shown that there exists an open set in capital Y, which is contained in y1 completely, and hence each point of y1 is an interior point. It means that y1 is an open set. Hence capital Y1 is open. Now I'll just take maybe 5 minutes more. Let capital Y2 be y such that fy is not equal to gy. So we will show that y2 is open. So this is basically complement of y1. We shall prove that y2 is open in capital Y. Now let y belongs to y2. Then and u be an evenly covered open set containing p composed f composed. So of course this f composed p y, right? So by p and containing this. Since fy is not equal to gy, right? There are disjoint open sets u1 tilde, u2 tilde in x tilde, such that this f y belongs to u1 tilde, gy belongs to u2 tilde, and uh, uh, p restricted over y, u1 tilde from u1 tilde to u, and p restricted over u2 tilde from u2 tilde to u is the homeomorphism. These are morphisms. Okay, because u is evenly covered, so uh, fp inverse u will be disjoint union of open sets. Of course, because u contains p composed fy, so of course, sorry, f composed py, right? This is nothing but g composed py, right? So fy and gy both will be in p inverse u. So they fy and gy, because they are distinct, they will belong to distinct disjoint open sets. Suppose they are u1 tilde and u2 tilde, right? Next, uh, uh, what we have is f inverse. Now f inverse u1 tilde intersection g inverse u2 tilde, right? So because this is an open set, this is an open set, this belongs to because fy is in u1 tilde, so y belongs to this. Gy is in u2 tilde, so y belongs to this. So y is common in this. So this is an open subset, an open subset of y containing small y and contained in y2. So why it is contained in y2? Uh, what we will do is, suppose that there is a point y naught in this intersection, which is not in y2, right? It means what? Fy naught equal to gy naught. Okay. It means what? It means that because of course, uh, so it is here. So fy naught is where? Fy naught belongs to where? Because y naught is here. Fy naught will be in u1 tilde and gy naught will be in u2 tilde. But fy naught equal to gy naught, if this happens, then u1 tilde and u2 tilde, they will not be disjoint, but they are actually disjoint open sets. So we have to have that this is the subset of this. Hence, y2 is open, because every point of y2 is an interior point, so y2 is open. Since y equal to y1 union y2, and y1 and y2 are disjoint open sets, right? We conclude that this y2 is empty because your y is connected, right? Because if y2 is not empty, y1 is definitely not empty, because this because this f and g agree at one point in capital Y, it means y1 is non-empty always. So if y2 also is non-empty, then capital Y will have a separation. It means capital Y is not connected, but it is already given that capital Y is connected, right? So y2 becomes empty. Thus y1 equal to y. This completes the proof. Completes the so I'll stop here.